We welcome you all to the FRB Origins panel discussion. We will go around and introduce ourselves. So I'm Pawan Kumar. My scientific interests and expertise are in FRBs and high energy astrophysics and cosmology. Since this is a setting where we don't get to meet each other face to face and in hallways or during coffee break, I thought that maybe I would just say a little bit about what I do when I'm not working on science and thinking about science. My hobbies, my interest is reading, literature, history, and politics. The last topic is, of course, been very frustrating and well, in any case. And the other hobby I have is figure skating. So let me just turn kind of to Ben.
Hi, everyone. So I'm Ben Margalit. I'm a postdoc at Berkeley. I work on time domain or transient astronomy in quite broadly in general. Yeah, so I guess things I do when I'm not doing research or astrophysics. Piano is one thing. I cook a lot, hiking, board games. Yeah. Wenbin?
Oh, hi. I'm a postdoc at Princeton. I work on theory, very similar to what Ben works on, high energy astrophysics. When I'm not working, I like rock climbing and taking care of my kid.
Mohit.
Hello, everyone. My name is Mohit Bhardwaj, and I'm a PhD candidate at McGill University, and also I'm a member of CHIME FRB collaboration. And when I am not in peak mode, then most of the time I'll spend either with friends and hiking. Recently I've been playing a lot of lawn tennis, and I'm also interested in politics and literature, especially horror. That's all right.
So with that introduction, what we are going to do is we have broken up the panel discussion into 5 segments on dealing with 5 different aspects of the origins question. And so we will go over, and I'm going to turn things over to Ben to get things started. So Ben, it's all yours.
Thanks. Thanks, Wenbin, for sharing. All right, just wait for the slides to come up. So I should say quite broadly that, the point of this discussion session is to have a discussion, and not just between ourselves, the panelists, but with everyone in the audience. So we really encourage everyone to participate. Don't be shy about raising your hand, asking questions. If possible, use the Q&A or chat, send chat messages to all attendees and panelists. But you can also use the Slack. We'll try to monitor that once in a while. Again, Q&A would be preferable. So, the point is to have as lively a debate and discussion as possible.
Ben, can I just interject? I think it's probably better to use the chat panelists and attendees because the Q&A is only visible to the panelists.
Got it. Thanks, Jason. All right. Great, so we have the slides. Thanks, Wenbin. Can we go to the first slide? All right, so I think the first thing to maybe kick off this discussion is to kind of look into the title of this session, which is, understanding the origin or origins of FRBs. But, the question comes to mind, what do we actually mean by origins? And you can mean various different things. And, different panelists might focus on different aspects of things listed on this slide, and perhaps people in the audience have other thoughts. So these are just things that occurred to me. A lot of us have thought a lot about the coherent radiation mechanism, basically, the detailed physics and microphysics of how you produce the FRBs. But if you take a step back, there are many things that precede this, so the origin can be what's the actual progenitor? So what object are we talking about? A neutron star, a specific kind of neutron star, if it's a magnetar, creating black holes, and similarly how these objects are formed. So, neutron stars can be formed in standard core collapse supernovae, but perhaps we need more exotic formation scenarios, for example, to explain the FRB in the globular cluster, and perhaps also to explain the demographics of host galaxies and offsets and things like that. So you might want to understand how the object is formed to also understand what object we're talking about. And then the other kind of intermediate step is, even if you understand what the progenitor is, or you have a good idea that these are, are very good candidate progenitors, in between that and the, very detailed nitty-gritty physics of the radiation mechanism, there's a lot of kind of general argument physics that we might be able to understand, even if we don't understand the detailed emission mechanisms, such as, what's the energy that we're tapping into? For a magnetar, is this magnetic energy reservoir, or is it spin down energy? What kind of processes are causing this energy to be dissipated, and so forth. And so there's a lot of different ways to approach this method, this question of what do we mean by origin. So I think that's sort of where I started with this. Wenbin, let's move on to the next slide, and maybe that'll kick off our discussion. So I think one thing that probably is on everyone's mind is this question related to the progenitors. So we know that a magnetar can produce an FRB. I think Brian Gensler was arguing that, maybe I'm wrong, maybe I'm just implicating Brian, it was someone else on the Slack, was implicating that SGR 1935 is not technically a repeater. But at least according to popular vote, through this poll that Emily nicely had in the Slack, SGR 1935 did produce an FRB. So then the question begs, right? I think everyone has been asking themselves this question: do all magnetars produce FRBs? And you can also flip that question around and ask: are all FRBs produced by magnetars? So those are kind of very broad, basic questions that you don't need to necessarily understand the detailed microphysics to start and try to answer. And there are various clues for and against either of these. So I think in order to engage everyone here, we tried to set up a few polls. And I think the first poll we have is on the next slide, which is exactly this. Oh, no, sorry. We have something in between.
No problem.
So
it's
Mohit,
after the slide, by the way. Yeah. So as Ben said, that there are so many questions we need to answer, especially about FRBs as a population. I just want to go one step back and then try to sort of make it clear that how this question that what FRBs are as a population evolved with time. Now, when in 2007, when the FRBs were when the first FRB was discovered, Lorimer burst, people were still arguing, and I think still in dilemma whether FRBs are astrophysical. Now, microwave open didn't make our life easier at that time. But as I think Thornton and others discovered more and more FRBs, the question changed. And then the thing is, because despite having follow programs for tens of hours, so in some cases even several hundreds of hours, we didn't detect a repeat burst. So the question is whether all FRBs are cataclysmic. So that was the question that was sort of popular during that time. And if you look at the papers, you see the papers on GRB FRB connections, GRB black hole connection and all that. But when in 2016, we discovered the first repeating FRB, FRB2021. Now, this question suddenly changed, and now people were thinking whether all FRBs are repeating source, and it's still a question. Now, later on, as more and more interesting observations come, and so we saw that this question actually evolved. For example, in 2020, the question when we detected the first periodic repeating FRB, now people were thinking that whether all repeating FRBs show periodicity of some sort. Maybe the time period varies, but are they all periodic? And then now, this year only, when we discovered an FRB in the Messier M81 galaxy, and that FRB was found to be associated with a globular cluster, an extremely old stellar population system. At that point, people were thinking whether there exists we need two different formation channels to actually explain this observation. And then there are many other questions that that have been raised in this conference. So I think it is important to see that this FRB as population, this question is evolving, and this is great because as more and more data we are getting, this question changes. So it is important to keep this in, I think, into our consideration when we are thinking about FRBs as population. So with this, and now actually we want, can you next slide, please? Okay, so one question is, neutron stars are definitely one of the most promising progenitor model right now we have, but there are more than a dozen of non-neutron star theories that actually you can find in FRB theory page. And then the question is, what about them? So the authors actually come up with some physically, at least in terms of physics, they come up with a mechanism that makes sense. So are they wrong? Are those mechanisms like some sort of have some sort of issues? So this is another question that we need to answer. If you go on next slide, let me play a devil's advocate, not exactly devil's advocate in this case. Present an argument. Now we have seen that we have detected SGR 1935 plus 2154, which is a magnetar. We all know that, independent of detecting these high radio bursts from this SGR. We knew this is a magnetar. And we found that there are radio bursts of energy around 10 to the power 38 ergs per second that this magnetar is capable to produce. Recently, CHIME actually discovered few FRBs where you see this quasi-periodic or sort of millisecond periodicity. Now, this tells you about, this actually is a very strong evidence that there is some sort of rotation, and because it's milliseconds, so neutron stars is one of the most plausible explanation for this sort of behavior. And if you just use, I know we don't know the host galaxy of this specific FRB, but if you just use the Mach-Watt relation and convert it, you find it at redshifts, the expected redshift is around 0.2. And at that redshift, the energy is 10 to the power 42. So if this is a neutron star, so we sort of have some evidence that neutron star can actually explain this whole range of energy, and there are millisecond temporal variability. So if you go with Occam's razor and say that, okay, almost all the observed characteristics can be explained by currently available by neutron stars, then why not to just assume that neutron star is the only FRB progenitor? Now, with this sort of idea, let's go and see what you guys think about this question. Can you go on next slide, please? Now, yeah, thank you very much. You need to present here. So we thought that why not add you also in this conversation? We don't really want to just speak among ourselves. We want you to participate in this. Now, because of this, we decided to have a live poll. Now, what you can do is, if you have a OR scanner in your mobile, you can just scan this OR code, and then it will point you to a web page where you can just click. And when you click on that web page, you can actually participate in this poll. Or else, what you can do is open an Internet Explorer and then just go to slido.com. And when you go to slido.com, you actually see that if you want to participate, you need to add a code. So that code is FRB2021-2B, as you can see on the slide, on the bottom left of the slide. Wow, and we can see people are participating. That's nice. We have only 2 votes now. So far 5, amazing, 6. It's nice to see that there is diversity. Cool. Let's wait for a couple more minutes and see what we get as the answer. What is the most popular answer? Get. I can see that there are many attendees, so we still need more votes. So please go to this web page and vote. That's a good point, Ben. We'll start the discussion just after this poll. 27. We need at least 5 more votes. Well, it looks to me that the first option is the most popular one. So you guys, as an audience, we think that no, not all magnetars can produce FRBs. And yes, almost all FRBs are produced by magnetar. That's an interesting observation. Now, there is no none of my business, or if I'm, no, that's fine. So can you go next slide? So with this, I think is no, my bad. So let's have a discussion before even you proceed. Or Pankaj, do you want to proceed with this slide, or do you have audience discussion?
Oh, actually, we can go to the discussion. I just changed and made it a discussion. So Wenbin, if you try going back to the previous slide, you will see.
Okay, meanwhile, I can just see few chat questions.
So we have here, because we have broken up our panel discussion into 5 different segments, we have allocated 10 minutes for this particular segment of questions. So please post your questions in Q&A or chat.
Well, Brian raised an interesting question. Brian, do you want to take the...
I can
invite him in.
Yes.
I think you can do that. Well, Brian said that, Brian asked this question, are all magnetars or young active, I'm sorry.
Brian, you can speak up.
Yeah, Brian.
Yes, so it was really just a clarification on the poll, but I was really fascinated by the talk earlier in the week on formation channels and globular clusters, which requires these things to have lifetimes of 10 to the 5 to 10 to the 6 years. And that's much longer than the age, the typical lifetime of magnetar, of an active magnetar. Of course, magnetars live forever in some form, I guess. So just the idea that there's an object that can produce FRBs for 1 million years, maybe there's something that a dark, dead magnetar can do, or maybe it isn't magnetars.
Well, magnetars probably don't live forever. I mean, the magnetic field decays with time, and the time scale for the decay of the magnetic field has a lot of uncertainty, but it could be something on the order of a few million years. So magnetars, I mean, neutron stars live forever, but magnetars turn into ordinary, well, neutron stars with modest magnetic field with time.
Yeah, but yeah, that's fair enough. I guess I'm also thinking about the multipole aspect of that. We have radio pulsars that have magnetar-like magnetic fields, and perhaps the difference between a magnetar and a normal pulsar is the complexity of the field. So do we expect the higher order moments to decay faster or slower than the dipole field?
Yes, it is the former. So higher multipole. So the smaller is higher multipole means you have a shorter length scale over which the field is varying. I mean, crudely speaking. And so that does bring down, so the smaller structure that you have for the magnetic field bundle, the shorter is the decay time. So it is true that higher multipoles will decay faster than the dipole would.
So I think that's just the real challenge for the globular clusters then, where you presumably need something relatively long-lived. And if we cannot think of any way that a magnetar can be a long-lived object, then there's something else that needs to be producing those FRBs.
Right, but Brian, that probably points to that this particular M81 FRB is not, the progenitor is not an old object, old as in Hubble time, Hubble time away or billions of years ago, but it was probably recently formed, maybe within the last 1 million years or so. Other people can pitch in. I can already see.
Yeah, Pawan, I think I think Paz is also making this point, and the point that Brian is making is not, I think that the magnetar needs to live for gigayears. It can be born recently through dynamical processes, but just the volumetric rate implies that it has to be active for order 100,000 million years, which is, you know, not crazy, but longer than magnetars in our own galaxy. So I think that's the issue.
Fair, we're fair enough.
And also the energy constraints we have for this, if this particular FRB is not really like strong or constraining. Like I think the brightest burst we detected, the isotropic energy is 10 to the power 37 ergs per second. So maybe you can relax some of the constraints on magnetic field or the age.
I see Zorwar has a comment about magnetic field decay. Zorwar, do you wanna speak up on that? We can unmute you. No pressure. Okay, great. Let's see. How do we unmute you? All right.
Right. Okay. Yes. As Sergey just said, that yes, there are these so-called low field magnetars that still have magnetic field activity. SGR 0418 is one example where there's a cyclotron feature at 10 to the 15 Gauss, but its dipole component is about 10 to the 12 Gauss. And just from the PP dot diagram, we know that magnetars decay, the track in the PP dot diagram, they decay in say 10 to the 4 years, and possibly related to the isolated neutron stars or the X-DINs as well, which have sort of magnetar-like fields but don't have magnetar-like activity.
In pulsars, people know it better. There is something called anomalous X-ray pulsars. It's switched behavior. They are sometimes radio pulsar, and then sometimes they show magnetar-like behavior. I don't know what are the age constraints on them.
Oh, so the anomalous X-ray pulsar, the AXPs are magnetars. They're unified by Vicky into the SGRs.
That's right.
Yeah,
that's right. So so maybe I'm using wrong word, wrong name for those sources. They sometimes just show pulsar-like behavior, but usually they are like pulsars. Or sometimes they show magnetar.
They're called the so-called transitional magnetars or high B pulsars. J1818 is one example. I think J1119 is another example. In the latter case, the actual magnetar burst suppressed the radio emission, and then the radio emission turned back on.
Okay, and what are the age constraints we have for those pulsars?
Those are all fairly young, very young systems, less than a kiloyear or a few kiloyears.
I see. Thanks. And I think we also.
So anyone want to comment or defend their position on, I think we discussed whether all magnetars produce FRBs, but whether all FRBs are magnetars?
So Ben, apart from none of my business, who's the last one, the option which gets the least votes?
Yeah, I don't remember what how the votes are distributed. I think the majority was saying that most FRBs are produced by magnetars.
Oh, they're agreeing, yeah. So those who think, I think the second bit also right, are almost all FRBs are produced by magnetars. So why we have so many non-neutron star models, what we can make of them now?
I think there are people in the audience here who have suggested alternate possibilities. And the panel would encourage those people to raise their hands or post something here, and we will unmute them. They can share their views directly if they would like to.
Yeah, Sergey and Brian both have their hands up. Oh, Emily now as well.
Unfortunately, on my screen, I don't see the, okay.
I can unmute Sergey. All right, you should be able to speak, Sergey.
I wanted to defend my view, which is actually the view of majority, no, yes. For the galactic magnetar SGR-1935, we see that the burst which produced the radio signal was anomalous. And it can tell us that there might be something specific about the burst itself. So maybe some magnetars just don't produce it. We don't know why yet. We don't have enough statistics, but at least we definitely see that not every flare of a magnetar produces visible radio burst. So maybe some sources can just avoid it forever or produce radio bursts so seldom that we can consider them not active in this respect.
So would you want to put your neck out as to what might be causing this specific magnetar, which is not particularly unique to produce bursts versus other ones?
No, I have no ideas. Actually.
Fair enough.
Should we move on to? There are 3 other people who have hand raised.
Yeah, here I can allow Brian.
Brian.
Hi. Yeah, I was just, since people were asking for alternative pictures, as I discussed in my talk, in the external models, there's some, you could have different central engines that are producing the plasmoids that nominally go out and produce a fast radio burst. And so, obviously one is limited in terms of what types of engines can produce transient relativistic ejections, but, it's not exclusively magnetars. The conditions in the quiescent jet of a black hole are not terribly different than in the wind of a magnetar. So anyways, I think at least in an external scenario, there could be different engines that are producing the shocks or reconnection. In magnetospheric scenarios, I could imagine as well, maybe there are other ways to produce it. So I think, I think that's my point is that there may be different, much in the same way with gamma ray bursts, how we have short and long gamma ray bursts that are, although there it's a little unfair because it really is very similar physics with merging neutron star, black holes and collapsars. But anyways, I think you could have, depending on the emission mechanism, you could have different engines that are responsible. Anyways, that's all I wanted to say.
Sure, thank you. It does, raise interesting questions as to what conditions are needed to produce these very bright, coherent, short pulses. We will get to that in a little while. So let's move on to Emily.
Yeah, hey. So I don't want to defend my position, but I do want to ask the people whose position is different from mine to defend theirs, which is so I was in the no yes camp, but I'm curious about this yes. Do all magnetars produce FRBs? I guess I would be curious for people who answered yes to that. So for the remaining like galactic magnetar population that we see, do we expect that, given a long enough wait time or, given enough years of all sky monitoring that we will see FRBs from every single magnetar in our galaxy? I'm just kind of curious. That's not what I expect, but I'm curious what other people think.
I see that Paz has a comment exactly about this. I don't know if Paz wants to speak out and defend it, but in the chat.
My standpoint is similar to Paz.
Oh, yeah, I was just making the point that SGR-1935 is not so unique compared to magnetars. Even if we think of things like giant flares, we didn't see one from 1935. It was relatively active last year when we saw the FRB, so it's reasonable. But it's 1 out of 30. It's not 1 one out of some enormous number. So if we wait long enough, it seems reasonable that we should also see FRBs from other magnetars, I think.
Bing Zhang has his hand raised. Let's go to Bing.
Oh, hi. Yeah, so I want to first make a comment regarding the progenitor and central engine or source, because you guys started to talk about progenitors. I think there's a slight difference there. When we talk about GRBs, the progenitors, we're talking about something before the jet is launched, maybe massive star core collapse or compact star merger. And the central engine is the aftermath, the magnetar or black holes. I think here we are mostly talking about, particularly this question is regarding the source or engine instead of progenitor, because magnetars can have several different channels of progenitors. So we are actually talking about the source. So that's my first comment. And regarding these different options, myself chose the second one, yes and no. So I actually was surprised to see no and yes. So if there is a magnetar that produced one FRB, why couldn't other magnetars produce FRB? Even if we haven't observed them, there's a mechanism for magnetars to produce FRBs. So at sometime during the life of a magnetar, that mechanism probably will make it and make FRB, probably just don't beam towards us. But looks like if one magnetar made one FRB, I would think that all magnetars can make FRB somehow. My position regarding no, which means, okay, are all most FRBs produced by magnetars? I voted no, because I was hesitating. So how to define that most? No is, I would definitely vote for no if it is are all FRBs produced by magnetars. Most is a sort of in the middle. How do you define most? But there are several different channels, as Brian talked about the creating X-rays. So I want to raise the possibility of interactions. So the cosmic cone, the very old version seems not to be working that well, at least for the periodic FRB, because they are a little bit too far away. But I'm thinking of binary neutron star mergers before the merger, pre-merger, say decades to centuries before the merger. There are a lot of interesting things going on, and something like reflections. It is still magnetosphere driven FRB type of the mechanism, but it's a very complicated system. The two neutron stars have different spin periods, have different, say, alignments, different spin axes. So the two magnetosphere can undergo very complicated interactions. In certain cases, reconnection will happen. Some magnetic flux would be annihilated, and some magnetic energy will be released. And after some time, maybe just like the solar 11-year cycle, the magnetic field might be restored after a while, and some magnetic flux will come back, and then they will start to interact again and produce repeating FRBs. So that is one of say, many possible channels of making FRBs. Yeah, that's all.
Okay, well, thanks, Bing. I think we will have more discussion about it a little later. We should move on because we have a number of different segments and topics that we would like to discuss. So this is a list of some of the major open questions. Why does a typical neutron star not produce a FRB? How confident are we that all FRBs are associated with magnetars? Any evidence for neutron star progenitor. We have discussed that to some extent already. This next one also we have discussed to some extent, but we can continue. You've got questions, we can continue entertaining that. So there are two classes of the radiation mechanisms, and we are going to turn to that and see whether, based on the data we have available, we can say whether the radio emission is produced within the magnetosphere of a neutron star, or maybe black hole, or outside the light cylinder. There are interesting questions regarding the periodicity that we now see on time scales of tens of milliseconds to several months. So that provides very interesting clue what that is. I think we should discuss that. Globular cluster hosting FRB was certainly a surprise, unexpected. So those are, if you go to the next slide, a little bit more regarding why does a typical neutron star not produce an FRB. We have got something on the order of 10,000 galactic neutron stars, which are younger than about a million years. And only 1 out of 40 magnetars in the galaxy seems to have produced a FRB. Again, there could be many, many different reasons for it. And I mean, the floor is open for discussion, but turning to the next slide, if we could, whether all magnetars go through a brief phase of FRB, maybe long phase of FRB, and what do we need? What do we need in the terms of data to be able to determine whether all magnetars go through this FRB phase or not, and what special conditions are needed for a magnetar to produce FRB is certainly one of the interesting questions. Let's go to the next slide. And turning to the question of the physics of the radiation. So there are these two different models. These are actually two different possibilities. One, that the radiation is produced inside the magnetosphere of a neutron star. Let's call it the near field model, which you see the sketch of that here on the inset here on the right-hand side. Or the radiation is produced far away from the neutron star, where there is an outflow, a jet moving with relativistic speed, carrying energy more than what we see in the FRB, and at some distance near the light cylinder, maybe outside of the light cylinder, that energy in the jet in the form of kinetic energy and the Poynting flux energy is dissipated, and a fraction of that is converted to the coherent radio emission. So that's the second class of model. We have got just a few slides to bring you all on the same wavelength. And so I'm going to turn to the next slide, and Wenbin will provide a brief discussion of the near field model that will be followed by Ben providing an overview of the far field model, and then we open the floor for 20 minutes for vigorous discussion regarding the radiation mechanism. Wenbin, it's yours.
Somehow this is supposed to move. Somehow it doesn't matter. So I'm gonna have 2 slide quick presentation on the near field model. This is just one class. Actually, even in the near field scenario, there are multiple choices within the magnetosphere. This is just one possible way. We think it's pretty likely. What happens is that there's a magnetic disturbance near the surface of a neutron star that excites horizontal shear waves. So these shear waves, this is supposed to be a GIF, which should propagate to the right, and this is showing the horizontal. This is the oscillation of a given point, which goes back and forth. These waves, they do not involve pressure, they involve compression or decompressing of the material. So there's no work done against gravity or the degeneracy pressure of the very dense material. It's just the shear waves. These are the typical velocity and typical frequencies of these shear waves. So these waves, they propagate across the entire neutron star. And you can imagine if there is a magnetic field line anchored on a given point on the surface, that field line is, the foot point of the field line is going to go back and forth as the shear wave propagates through. And that will launch Alfvén waves into the magnetosphere, showing over here. And only near the polar cap, where the field lines can extend to very large distances. It doesn't have to be within the polar cap where the field lines are open due to rotation. As sufficiently close to the polar cap, let's say within 0.1 radian from the polar cap, the field lines that is sufficiently extended such that the Alfvén waves can reach to very large distances, tens, hundreds of neutron star radii, where they can get charge starved. And that, we believe, that can generate FRBs, because at charge starvation, what happens is that the Alfvén wave loses its eigenproperty as Alfvén waves. The charge number density is too low to support the Alfvén identity of the waves. What happens is that there will be an electric field parallel to the magnetic field, and that can accelerate particles and hopefully bunching charges up so that they emit coherently as FRB waves. So here are the pros that I think of this model. That I think the magnetic disturbances is very natural. It's very natural that the disturbances launch shear waves and then Alfvén waves, regardless what happens to the Alfvén waves later on. And then the Alfvén waves do carry enough energy to generate FRBs. And this model, if correct, if the emission, which we show to be reasonably, it's in the ballpark of the observation in terms of the millisecond duration and X-ray counterpart variability, polarization, and even the cluster of bursts. You can imagine that the trigger here can happen periodically because of the shear waves. Let's say if the neutron star has some global oscillation modes, then that can periodically trigger these Alfvén wave bursts. So the con of this model is that we have not demonstrated that charge bunches really form at the charge starvation radius. That's to be worked on in the future. I'll turn this to Ben.
Thanks, Wenbin. Okay, yeah, so just a very, very brief 1-minute overview of the far away or synchrotron maser model. So in a progenitor agnostic way, the essence of the model is shown in the right side of the plot. Basically, all you need is a relativistic magnetized shock. So those are two quite generic conditions that are present, we think, in lots of astrophysical settings, specifically probably in the setting of a magnetar. If you have these conditions, then once the shock runs into this magnetized upstream medium, then a lot of work has gone into showing that you produce this coherent maser, synchrotron maser emission. And so this is work that has been led recently by Lorenzo Cerroni and many others. And so we know that you can produce these coherent radio waves through such processes. And then you can ask, well, what produces these relativistic flares that run into some magnetized medium? Well, in the specific context of a magnetar, basically you go back to Wenbin's previous picture. So you have kind of the same idea, same general story. You have a starquake that shakes the magnetic field lines, that launches Alfvén waves. The only difference is that in what Wenbin was showing, the idea was that these Alfvén waves become charge starved and they're produce the coherent radio emission in the outer magnetosphere. In the scenario that kind of we're envisioning here, these Alfvén waves eventually launch plasmoids. So they basically tear the magnetic field lines and launch relativistic plasmoids. And this is actually supported by recent work by simulation. So this is, for example, simulation by Yuan et al. And she had a very nice talk discussing her results. Wenbin, can we move to the next slide? Thanks. So I think some of the nice features of this specific model is that it seems like it's a very robust process in the sense that the conditions that you need to produce this are quite generic. All you need is a magnetized relativistic shock. There's nothing here that we don't, understand in terms of the physics. And this is also directly supported by first principles calculations. So namely, if you solve Maxwell's equations on the computer, if you have these particle and cell simulations, such as those performed by Lorenzo Cironi and others, you just directly find from first principles that this is in fact happening. So it's not just, kind of pen and paper ideas, but it's actually proven to work, at least on the computer. And furthermore, as I just discussed, Yaji Wan, who had this very nice talk in plenary session 5, showed in her work that these magnetar quakes can actually launch such relativistic plasmoids. And then the final point that I just want to reemphasize, and I think we've talked about this before, is the fact that this model actually predicted the hard X-ray counterpart seen in the galactic FRB. So it predicted both, the hard spectrum and the time scale and so forth, and the energetics. So I think to me that's quite, either an amazing chance coincidence that we really just won the lottery, or I guess maybe, inversely won the lottery, if this is just a coincidence and not telling us something important. But to me, this seems quite indicative. Pawan, I think you're muted.
So, okay, thanks Ben and Wenbin for providing a brief and nice summary. Open the floor for questions about the physics of FRBs for 20 minutes. So please raise your hand or post your
question. Has her hand up.
So I see that Zorara mentioned the question that it's uncertain if magnetospheric Alfvén waves can be excited. His point of view is that when the plasma has really high density, because in the pair fireball is Compton thick, actually in that situation, in the situation where the plasma density is very, very high, that's exactly the situation where Alfvén waves would be launched, would be excited. Because Alfvén waves can only exist in the situation where it's not charge starved. There is plenty of charge to short out any parallel electric field. We're thinking when the Alfvén waves gets to very, very large distances, let's say tens to 100 neutron star radii, where the plasma density might be much smaller, and then the Alfvén wave may get charge starved. If the Alfvén waves never get charge starved, it will become nonlinear, like in Yaji's simulation, and that will blow away a plasmoid to infinity, basically.
I saw that Zorwar put his hand up. Maybe, Zorwar, do you want to comment directly on this?
Sure, yes. So we know from observations that magnetar bursts are very Compton thick, and you don't actually need a very high charge density to make them Compton thick because of resonance scattering. So in that sense, the particles and the radiation are strongly coupled, at least parallel to the field. So it's uncertain to me that you will have at least normal Alfvén modes. The second point is, okay, I think Alex Chen and recent collaborators have shown that at least the Alfvén waves are not very efficient at converting into coherent radio emission.
Right, yeah, that's another very interesting point.
I'm aware of that work. We're still working on how the Alfvén waves getting to large distances can be charge starved. We still believe that the charge starvation should happen, but exactly the plasma physics near the charge starvation location, right now we have not worked out, but we still believe charge starvation should happen and strong electric fields will be generated.
Maybe I can inject some thoughts here on this particular topic of Chen et al. And that is, it's a nice work, good simulations. But here is the thing, their picture is, what they have simulated is that you have an Alfvén wave which is moving outward, and it is carrying these charged particles with it, electron and positron, with a certain Lorentz factor. In their simulations, their Lorentz factor, if I remember it right, is something on the order of 10 or few tens. Now, as the wave, Alfvén wave is moving outward, carrying these electron-positron plasma, there will be a lag because alpha wave is moving at a speed which is very, very close to the speed of light. Electron-positrons are moving with a Lorentz factor of 10. So if the wave travels a distance, call it d, then there is a electron-positrons would have traveled a distance which is smaller than the alpha wave by an amount which is d over roughly 100, if the Lorentz factor of the electron-positron is 100. And that will develop. So that will develop a deficit in the current density that is provided by these charged particles, which is small. If you only travel a small distance of d, say order of a wavelength or a few, which is what they did in their simulations. However, if you allow the wave to travel for distances which are tens or hundreds of wavelengths, which is what realistically must happen, then you will have a much stronger current deficit that will develop. And that can only be made up for or compensated for by the displacement current, meaning dE dt. And so it's very difficult to avoid producing a strong electric field here, even in this simulation situation of an alpha wave, which is carrying electron-positron pair with it. It can do that for a certain distance, but not long and large enough distance that is being, well, needed for the realistic magnetar situation. So let's take other questions and comments. And Emily and Bing, your hands are raised, but I'm not sure whether they are raised from the previous time.
Oh no, I have a new thing. So I was wondering if you can you go back a couple of slides? Is that possible? Oh, sorry. Yes, here. Yeah, so I just had a question about the shock model with regards to SGR 1935. Maybe this is like a pretty simple question. I just don't quite understand. So if the SGR 1935 FRB is produced by forward shocks or from the synchrotron maser model, would you expect to be able to see, like using multi-wavelength imaging or something like that, to actually be able to see the shocked medium, or to be able to see like the material around the magnetar that's, you know, I don't know like what it would look like if it's too close to the source to actually like see it in multi-wavelength imaging. But since it's so close by, maybe, yeah, I was just kind of curious what having something so close by could tell you about the shock model and the material around the progenitor or around the magnetar.
Yeah, that's a great question. So I actually saw that Brian raised his hand. I was gonna defer to him just to get other people to speak, but I can also answer this. So I think the point is that the amount of material that you need upstream is quite small. These are relativistic plasmoids, but you know the amount of mass that they have is very small. So you basically slow them down. It's kind of like running, I don't know, relativistic flies into a wall. You don't need a lot of matter upstream to stop this. So I wouldn't have much hope of seeing this circumstellar material directly. There are other aspects such as whether or not you inflate a nebula, kind of akin to a pulsar wind nebula from the activity of the magnetar. That's an interesting question, but that I think is somewhat separate than the actual, direct upstream medium to which the bursts run into.
Yeah, I also have a new question. So I don't know whether Yajie Yuan is on the call. Yesterday I forgot to, it's a very nice talk, forgot to ask the termination Lorentz factor of the plasmoid after the alpha wave driven acceleration. So that is also related to a question to Wenbin. Your recent very nice paper regarding the globular cluster FRB, the 15 nanosecond variability timescale is used to favor the magnetosphere origin and disfavor the shock origin. My understanding is I don't know whether if the Lorentz factor is arbitrarily large, can solve the problem for the shock model, or the shock model has some intrinsic deficit, even if the Lorentz factor is say 10 to the fifth.
As far as I know, the shock model, the Lorentz factor combined with the radius of emission keeps the duration of FRB. So let's say if the radius divided by gamma squared, which is the time scale that's involved, if we were to use that for the variability time, then what sets the duration is a much larger time scale. So it must be somewhat of a persistent ejection. My understanding is that if the time scale set by the radius and the Lorentz factor is the duration, then you cannot avoid, let's say during a very short amount of time, you cannot avoid seeing the entire 1/gamma cone of the emitting surface, right? And that will make the duration very long compared to 15 nanoseconds.
Well, there are also propagation effects. So Manuel Sabachi had this very nice paper that showed that you can get actually microsecond structures just from propagation effects. So it's not entirely clear, you know, yeah.
Well, what if it's similar to the GRB internal shocks, and so each emission unit is like 15 nanoseconds, and the entire duration is defined by the central engine. Is it still possible?
Right. So go ahead. No, Ben.
No, go ahead.
No. I defer to you. Go ahead. I will go after you.
Well, I was just going to say very briefly, just remark that, you know, on observational grounds, right, the variability timescale in GRBs over the duration of GRBs is order hundreds, right? And that's sort of similar to what we're seeing at the moment for FRBs, at least some of them. So it wouldn't be crazy to think about that, yeah.
Right. So Bing, I think this question of an internal shock, right, that you say, could it be that this synchrotron maser model is not in an external shock, but it's operating in the so-called internal shock? Now the audience, this particular audience may not be familiar with the internal shock per se. It's a very simple concept that you have got an outflow which is not steady, which means the Lorentz factor is not constant in time, but it varies with time. And hence, a faster moving material that is ejected a little later is going to catch up with the slower moving material that was ejected a little earlier, and they will collide, and there will be a shock and a resulting synchrotron maser. Now, this is something that was looked at, and I see Brian, he is here in the audience, or he was in the audience, and I can certainly amplify and say something, but it may be better to come from, you know, other people. So Brian, are you still around?
Yeah, I am actually. I guess I'm unmuted.
Okay, you are. So
I just wanted to say, yeah, I mean, I don't know if it was presented in this conference, but Lorenzo, you know, has showed even in the post-shock frame, basically the FRB waves have to outpropagate the shock. And so there is a beaming of the emission even in the post-shock frame. And so if you calculate the time, you know, that sort of duration of the FRB, you know, the deceleration time, you know, I think you can in principle get variability on a shorter time scale, because even in the post-shock frame, there's a beaming effect. But the problem is that the downside of that is that the efficiency of the maser drops as 1/sigma. So there's a trade-off. You could get rapid time variability, but then you pay a price in terms of the energy budget of the central engine. So I would be uncomfortable arguing we can get nanosecond time scale. You know, many tens of microseconds, hundreds of microseconds, probably not crazy for a millisecond FRB. So anyways, I think there are ways to get, you know, and the other thing I would just point out is that these shocks are almost always in a regime where they're radiative. which means that they're very, there's a lot of potential for instabilities that I don't think have been fully looked at. So I don't think we expect a nice smooth shock front that's all emitting. There may be some variability at the shock front that hasn't been explored. But anyways, that's all I want to say.
Brian, is there specifically the point that being raised is the internal shock? And I thought that you and others in Colombia have looked at the internal shock kind of a scenario, and there are difficulties and problems with the internal shock scenario. Am I mistaken about it?
Oh, internal shock meaning two flares of kind of comparable Lorentz factor.
That's right. That they are colliding.
Yeah, I think we need a large contrast between the Lorentz factor of the upstream and the ejected one. It's been a while since I looked at this. I don't
No, that is one of the problems. So you need a large contrast. And the trouble with large contrast is that these things will collide at a small distance. So let's take two flares, which are separated by a time, which is some fraction of a millisecond, with a large Lorentz factor contrast. And that contrast Lorentz factor ratio, call it, delta gamma ratio wise. Then they will collide at a distance, which is going to be something on the order of the delta t, the time separation between the ejection of the flare, divided by this Lorentz factor contrast squared, which really comes down to the lower Lorentz factor, lower of the two Lorentz factors. And so it is going to collide at a short distance, where you will have the induced Compton scatterings would be a killer. There are other things that become serious problems.
Yeah, the analog of the model we've been arguing is more akin to an external shock. But what I'm saying is that because it's a magnetized, highly magnetized external shock, you can still get variability on a timescale shorter than the envelope of the shock emission because of this beaming effect.
I understand. No, I fully.
But you're right. Yeah, you're right. I think the internal shock scenarios probably have problems, but I can't say I've done an exhaustive study. It sounds like you have.
So that is kind of the answer. Thank you, Brian. Yes, and so that's the situation being regarding the scenario.
I see Andre raised his hand.
Yeah, let's go to him.
Can someone unmute him?
Yeah, Andre should be able to talk.
Okay.
Andre,
can you hear me? Yeah.
Yeah, we can hear you.
Yeah.
If you don't mind speaking up a little bit,
okay,
that would be great. Yes.
Yeah, just a quick remark that the shock, of course, forms very quickly, but the radius at which most of the energy is deposited by the ejector material, which is dominated by magnetic energy. This radius at which most of this energy gets deposited into the shock is large, up to 10 to the 14 centimeters. And so that's also the characteristic radius at which this blast wave is going to produce gigahertz emission, roughly 1 AU, roughly speaking. So I don't think there is any problem with kinematics in the sense of, with which radius and what time scale you would get overall. What really is a problem is the short time scale variability that we see, but that's been brought up already, like how the blast wave becomes so intermittent in emitting these variable light curves of FRBs. And the biggest question here, I think it is, my view, is actually the propagation effects, which we don't really understand. It would be really important to rule out, the big role of propagation effect. Then we could focus more seriously on the physics and instabilities of the blast waves, and because it's a complicated topic to study. Yeah, thank you.
No, Andre, thank you very much for that input. I think there's not much that I need to add to what Andre has said. His basic point is correct, in my view, goes without saying. If most of the energy is deposited at this radius of AU, then clearly the time scale is set by AU divided by gamma squared C. And so that's a long time scale. Propagation effect, yeah, sure, can do it. But the specific propagation effect that we have looked at it doesn't seem to cut it. So this very interesting instability that lasers and masers suffer moving through a plasma that was analyzed, very good work of Sobachi and collaborators, doesn't seem to cut it. It doesn't seem sufficient to be able to produce variability on a time scale of 100 nanoseconds. It can surely do it on a time scale of a microsecond. It can. Could there be other instabilities? Well, in principle, not knowing what may be there, I can't say that that is ruled out. All I can say is that based on the concrete things that we know, I have seen nothing to be able to, no propagation effect I have come across physics-wise that can give us tens of nanosecond variability. And it would be great if there are people who can contradict me and say, well, here is the thing that I have overlooked. We have to keep also an eye on these chat boxes and questions to make sure that we are not overlooking interesting thoughts and comments and questions posted here. So I'm certainly counting on my fellow panel members to ensure that nothing is slipped through us.
I see that there is an interesting debate on the number density and the number of magnetars in globular clusters versus the number of magnetars in the galaxy, and what's the ratio? Can it be 100? Can it be 1% or 10%? I see Wiley is asking some question. Maybe you want to speak up.
Wiley Penn, can you unmute yourself and please make your point?
Okay, can you hear me now?
We can hear you
good.
now.
Yes, I mean, I'm not sure that there is any requirement that probable clusters had any core collapse supernovas in the last 100,000 years because they're very old. Not to say it couldn't happen, but I'm just saying the uncertainty is large, right? I mean, while I think we should leave this as a known unknown as opposed to saying it's a known. So I think the rate could be 0. I mean, that allows, not to say that it's required.
Well, I don't know if you have finished making your point. I don't mean to interrupt. Yeah, of course. Core collapse, no, but there are other ways of forming.
I saw Searle's comment, the AIC, indeed, but I think these are, again, possible. I'm not sure that they are required to have happened. I'm just saying it's uncertain. To me, it seems it's uncertain, not to say it's known to be, just, like, unless people think it is absolutely known that there is a known rate of magnetar formation in globular clusters. Otherwise, does anybody say it has to be non-zero?
I see Stir raised his hand.
That would be, please unmute him.
Yeah, earlier in the chat, I pointed out there are 3 high field young pulsars known in globular clusters and M28 and others. So there clearly are young pulsars being recycled. And they have magnetic fields that are well above the spin up line, spin down ages less than 10 to the 8th years. And so they're clearly forming, probably not by core collapse, because those are, there's no gas in the clusters. But AIC, I would say, is plausible for those. And if you can make 3 10 to the 9 Gauss fields, maybe you can make 10 to the 13 Gauss ones too.
Thank you. Thank you, Star.
So I personally feel that since we don't know these AIC channels, the rates of them, we should keep an open mind that they may exist. And since we have a prior that FRBs may be generated from magnetic energy dissipation from these neutron stars. So it will be really, I would say, we shouldn't really overlook that possibility, because we have from other observations of FRBs, it may well turn out that FRB provides the excellent probe of these processes. This is just my personal thought.
We have Wiley Penn has raised his hand. I don't know if it is from before or now.
Sorry, that was from before.
Okay. Maybe we should proceed, that is move on, because we have got 3 other topics that we would like to, get some discussions.
We should do the poll.
Oh yes, let's do the poll. Thank you. But let's make sure, Starl had some comments here posted. Let's just make sure that we are reading this thing to make sure. Yes. Okay. Thanks, Starl.
I can see that there are already 4 people voted. That's great.
Okay.
So you can use the same link. Yes. Let's see who wins. Wenbin, do not click, because if you click, you will see the results.
If I click?
Yeah, don't click. No, don't move to next slide, or just
okay.
Let them vote and see now what people.
Wenbin, you can't vote apparently. Your vote is lost.
Yeah.
Are panelists supposed to vote?
No, I'm not planning to vote.
Yeah.
We should have asked the question, how much money are you willing to bet on your answer? Is it more than 10 cents?
We can ask this question to our panelists, because Ben, Wenbin, and Pawan, you 3 are like theorists, and it's your models. Tell us how much you want to bet.
I want to bet $10 on the near field model.
Well, I've heard that the correct, game theory way is to bet against yourself. So I should bet on the near field model as well. So if I lose, at least I'll gain something.
And see, if the answer is none, both, and I don't want to make any wild guesses, then I'll win. I'll get the money.
Should I reveal?
It's 25, you guys. We have more participants. So last 10 seconds to everyone, please vote. Let's see how productive our discussion were. Once, twice, 26. You can if you want.
This is just a personal opinion. Nothing really so serious about, you vote and you have to believe that or something.
Did you play?
Yeah, let me click.
Oh, wow. I was so close winning $20, but now I lost. Cool. So I think everyone decides the near field looks promising, but still there are like both as well, the option field.
Yeah.
I don't know. Yeah. Let's see what you guys come up with in the next 5 years.
Yeah.
I think Brian raised an interesting point in the chat, which might bring us to our next question, right? Which is whether or not we can actually settle this.
We will have another poll on whether we can settle it later on. Okay. Pawan, back to you.
All right. We are going to turn to the next topic, which is very closely related to the discussion we had on the physics of FRB radiation. Now the question is, what observations do we need to narrow down the physics of FRB radiation? Here is a list. It's again a partial list. We don't know what exactly will be kind of a smoking gun signal that will tell us what nature is doing. But here are the things that are surely going to be enlightening and help narrow down these two different possibilities: variability, temporal variability, spectral properties, polarization, radiation at other wavelengths, and also local stellar environments of nearby FRBs. Let's get to the next slide. We have already discussed that in some detail. This is simply to kind of remind us that we have a variability on time scales of hundreds of, 50 nanosecond to tens of microsecond. And here is a table not meant to be a complete list of everything that we know, but 4 FRBs listed here. The key thing that I want to draw your attention to is the duration of the FRB divided by the variability time. These numbers are from kind of order 10 to several hundred. And that does seem to contain very interesting information. Modulo the propagation effect, very interesting information about the radiation mechanism and the place where the radiation is being produced. The question for observers is, how generic is this fast variability? What fraction of FRBs have this delta T over T much smaller than 1? So this is a challenge to my observational colleagues. Quantify it. Tell us what fraction of FRBs have this very fast variability. Is it just a minority of these 3, 4, 5, or it's more general than that? Let's go to the next slide. There is a similar thing on the spectral side of things. How generic is it that we have very narrow spectrum? This is something that has been shown in this conference before. This extreme case of this SCAP FRB 2019-07-11, which has a spectral, this is narrow spectrum of 65 megahertz at 1.4 gigahertz that you see here. I mean, that's ridiculously narrow. There is no mechanism, almost no mechanism that I can think of that is going to give you this very narrow spectrum. Clearly another clue to what may be going on. Let's turn to the next slide. When we see the spectrum turning off suddenly at low frequencies, that's another interesting clue to what may be going on. Here, it could be scintillation responsible for the fact that for this galactic FRB, we see no flux or zero flux, close to zero flux at low frequencies, lower frequencies. For the second pulse, when it was present in the same frequency band for the first pulse. Very difficult to see scintillation doing it, yeah? We can't blame it on scintillation. Let's turn to audience, but here what we have got, before we turn to that, Paz, if you are around, Paz Binyamini?
Yeah.
If you're around, can I call on you, can the panel call on you to provide some perspective about how small delta T over T can be and how quickly spectra can turn off? Can
I share some slides?
Absolutely, yes. We are going to. Ben, can you facilitate that?
I'll try, yeah. Just a second. Paz, I think you should be able to now as a panelist. You're still muted, Paz.
Oh, sorry. Do you see my slides?
Yes.
Let's see. Let's go to presentation mode here. So yeah, there is a bunch of these questions that Pawan just mentioned that we looked at in this work from last year. How quickly the spectrum can cut off, how quickly the emission can cut off, what kind of variability you can get, specifically looking at those models, the external models, where you have a synchrotron maser that produces the emission at a large radius. There is a characteristic timescale, which we already discussed here, so I won't go into the details of it again, which is R/2c gamma squared. One can get things which are shorter than this timescale, but generally they require a reduction in the efficiency. And broadly speaking, the factor by which you can improve on this timescale is the factor by which at least you reduce your efficiency. The other point which Pawan already mentioned is about the delta nu over nu being very small. And one more point maybe to mention here is about the high latitude emission. So this is inevitable that if we have emission coming from this relativistic shell, then the photons that are emitted at higher latitudes will reach us at a later time at lower frequencies with a somewhat lower flux. This can be worked out even for a delta function spectrum, delta function in spectrum and in time. There is still an inevitable minimum level of flux that should be observed at some later time at some lower frequency, which goes as this x to the -2, where x here is the ratio of the times that you're looking at, or ratio of the frequencies that you're looking at. And Pawan already showed this missing flux in the SGR 1935 burst, which appears to be in some contention with this limit. And there are also some cases from 121102, which are similarly kind of challenging this limit. So what are some ways out? There are some ways out in terms of propagation effects. They typically require some kind of very special conditions, at least the ones that we looked at. And there's also ways out in terms of things that have to do with the emission at the site itself. But again, it comes at the price of efficiency. So I won't go into all the details here. I don't want to give a talk or anything here. But let me just mention this point about the propagation that was brought before, which was this effect where the wave can be fragmented along its way to the observer. But again, this has a limit on how short of a time scale we can get from that. There was the point that Brian mentioned before, where we can improve the time scale by a factor of 1/sigma, but this comes with a reduced efficiency. More generally, you can imagine the source being sort of clumpy in such a way that you're only seeing emission from these clumps, but this always comes at the same price of efficiency. So really, not to bore you with the details, you can look at the paper if you're interested. This is the trade-off. The trade-off is if you want short variability, it comes with low efficiency. And if we have something from the emission mechanism that tells us what the total energetics are, what are the possibilities in terms of efficiency, this will limit if these things are viable or not. And I don't know if I should go into any of these other possibilities. I think maybe I don't want to take too much time.
If I may suggest, yeah, let's leave it at that pause. The reason is, let's just hear from the audience. The floor is open for your questions, comments, criticisms, what have you, and let's hear from you.
Well, we can proceed as well, Pawan.
Let's wait for a minute. Just making sure that maybe some question may occur to some.
I think Andre
I see Andre. Yeah.
Andre, please unmute yourself.
Okay.
Yes.
Yeah, just to entertain the discussion. I think since we're talking about external shock models right now, the efficiency.
Just to make sure, I don't mean to interrupt. I think it's more generic. I think the discussion here is very generic, not external shock per se. These considerations are basic physics consideration that apply to any and every model. But with that, please go ahead, Andre.
Yeah, so the issue came up with efficiency and how the efficiency would drop, how you would trade it for shorter millisecond, for shorter variability timescale. So the question is, what is the efficiency that one would need? If we start out with the magnetar, which is hyperactive in particular, because for brightest bursts, which are far in distant galaxies, we don't really know the sources, but I think personally that these are very young magnetars, most sources, and then they're extremely magnetized, and they're, for that reason, extremely active. So but even our galactic magnetars, they have a lot of energy, magnetic energy, up to 10 to the 49 probably. I think these young and hyperactive magnetars could easily have fields 10 times stronger, a few times 10 to the 16th, and then the energy budget would be 10 to the 50, 10 to the 51 erg. And so I don't think there is an efficiency a problem for a broad class of models as long as the efficiency exceeds small value, 10 to the minus 6, 10 to the minus 5. My impression is it would be okay. Is it right? Is it consistent with what other people think?
So yes and no. See, if there is a source which is just one-off source, right, then the efficiency can be small. And I don't see a problem with that. If the efficiency is 10 to the power minus 6, the issue that arises is, where is, a million times more energy, which channel, which wavelength band is that showing up, right? So that's a natural question that arises. Now you can hide a lot of this energy in the sense that if it comes out in the X-ray, well, that's easily hidden because the energy in the FRB channel, the radio channel, is so small, even for the brightest one, that you can easily hide a million times more energy in the X-ray for one off burst. The problem becomes more serious when you have a source which is repeating. Then the energy adds up. And over a period of, if the source is active for a period of 100 years or 1,000 years, then it starts to become excessive. And there is a problem for the energy budget. Let me know if I'm missing something here, Andre.
According to my estimates, 10 to the minus 5 efficiency is completely sufficient for the energy budget of the very active, even frequent repeaters. If the magnetic energy is something like 10 to the 50 inside the magnetar, which is what would be expected, it could be even higher. The efficiency, of course, depends on the model. What is a good number? Is 10 to the minus 5 is a good number for magnetospheric emission model or for external shock model? For external shock model, we know what the efficiency should be. It's 10 to the minus 3 divided by magnetization of the upstream medium. And the magnetization, at least according to my estimates, is like 10 or maybe 30. Yeah. And so it does give efficiency, which is maybe even one order of magnitude higher than you would need. So I think you can afford losing efficiency by an order of magnitude to trade it for shorter time scale. Yeah, that's what I think.
Let's
we also haven't
been. Oh no, go ahead, Brian.
Oh no, I was just going to say one thing that we haven't even discussed, beaming. I'd be interested in people's thoughts about that as well, but perhaps we can let Bing talk, and maybe he has thoughts about that too.
Oh yeah, so actually I'm going to comment on the efficiency and beaming. So for the recent paper, the 12-1102, the detection of more than 1,600 bursts within less than 2 months, if we take efficiency as 10 to minus 4, and if we assume that there's no global beaming, so the individual bursts are beamed, but there are, say, suppose the beaming factor is FB, but there is 1/FB other FRBs directing to other direction, which means beaming does not enter the problem, then during that less than 2 months, that source is already, I think already, we have calculated, we already emitted 1% of the magnetic energy if the magnetar has a B field 10 to 15 gauss. So that's the numbers. You can play with the global beaming, which means that individual bursts are beamed, but globally they're also beamed within a certain, say, solid angle. But that one cannot, according what we know about pulsars, cannot be too small. So maybe you can gain another order of magnitude back, which means you can make it like 0.1%. But if the efficiency is 10 to minus 5 or 10 to minus 6, that is very difficult. So that is a comment on the efficiency and the beaming. And also regarding internal and external shocks, there's another consideration is the Sater-Trombone effect, because repeaters do show that. And as far as I understand, external shock model can do that. Internal shock model does not have control to reproduce that. On the other hand, the internal shock model probably have a better chance to interpret a small variability, but the external shock model does not. So that's my comments.
Thanks, Bing. Other people would like to chime in? Well, we'll wait for maybe a few more seconds and then turn to the next.
Yeah, just to comment on the beaming, at least for SGR 1935, I think we have some evidence that the beaming is not tiny, because we saw 2 bursts separated by about 1% of the spin period. So unless the orientation is very favorable or unfavorable, depending on your point of view, it will probably mean that the beaming is greater than 1%. Another constraint comes from the fact that there's some evidence that the X-ray burst that was associated with the FRB in 1935 is special in terms of its spectrum. And it stands out of the other X-ray bursts in that forest of bursts. So that suggests that there weren't many other FRBs coming from that burst storm that we missed, and therefore that the beaming is unlikely to be very small.
Interesting point, Paris. Anyone else who would like to chime in? Should we move on in that case? So that's another. So we have variability, we have spectral properties. We have a number of cases now where we see very closely spaced bursts. Again, this is by no means meant to be a exhaustive list of all the observations. This is just a sample of it. Once again, this galactic FRB with 2 pulses separated by 30 milliseconds. And the more recent one, just posted a few weeks ago, with periodicity. Now on time scales of anywhere from the weakest signal is like 5 millisecond to this one here, the strongest signal, the left panel here, which is on a time scale of about 100 milliseconds. That provides an interesting clue to the central engine, so to speak, and the radiation physics. So let's go to the next slide. That is to say, that's another clue we should discuss. And what we should do is maybe wait for and include the polarization, which we haven't even touched on. And it contains very interesting properties. So now the floor is really open in the terms of jumping in at any time. There are a number of puzzling observations, some of which we have already discussed. Morphology, difference in morphology of repeaters and non-repeaters, weird spectral features, very diverse polarization behavior that has been discussed at this conference. And we have a number of slides here that you have seen numerous times. So there is nothing new in those slides, but that is puzzling, interesting puzzle. And the absence of a cutoff, low cutoff in the luminosity function is yet another one of those things that is contains interesting clues and begging for physical explanation. So with that, we can just quickly go through the next few slides, but very quickly because people have already seen it. And maybe Mohit, maybe very quickly to just remind the audience.
Sure.
Just in a minute, so that we can spend the remaining 20 minutes for just open discussions.
Absolutely, yeah. I just want to say that, so there are many observations where both the models, mesosynchrotron as well as coherent curvature radiation, they don't provide, you can say, direct evidence for these observations. The first one is why repeating FRBs have larger burst width and smaller emission bandwidth compared to one-off FRBs. Can you go on next slide? Now, steep narrowband structures that we have seen in many FRBs. I've just showed two waterfall plot on this slide, but there are many. So there is no, I think, convincing sort of explanation of how these knotted narrowband structures form in the first place in these two models. If you go on next slide. And then diverse polarization property. As you know, both of these models predict 100% linear polarization because of the configuration they invoke. But we have observations, or we actually have detected a few FRBs where we see circular polarization. I've just mentioned a couple of them here. And there are at least one FRB where we saw no polarization at all. It's completely unpolarized FRB. And there are several FRBs where we actually saw both circular polarization as well as linear polarization. So these observations must be explained by these models. And I think these are, as Pawan said, these are open questions. If you go next slide. So here we just discussed, I think Pawan already discussed this thing, variable polarization angle. And if you go next slide. And we do see that many of the repeating FRBs have 100% polarization flat PA. But I think this is also discussed. If you go next slide. Now, the last bit that actually Pawan said is whether there exists low luminosity cutoff. From observations, we cannot say at least. And there are FRBs. For example, if you consider Nemo et al. Detections at around 60 or 90 nanoseconds, and you convert this spectral luminosity into energy, you find that the energy is equivalent to the energy that we see in the case of less luminous SGR bursts. So it's way less than 10 to the power 36 or 37 cutoff that I think in papers, there are several papers where it is proposed. So we still don't know whether there exists one or not. and whether theories can come up to actually explain this observation. So we need more basically observations to check this. Next slide, Pawan.
So, right, so I think we should just simply open the, now just have the questions now. There is no, the demographics and host galaxy properties. I mean, the audience knows that. So, so let's make sure that the remaining 17 minutes that we have is really devoted to having questions and discussions here. So
I think Brian, Brian has had his hand up for a while.
That's right. Brian, please go ahead.
Okay, thanks. I think this is in response to something raised by Pawan a bit earlier, which is how constraining very shortly spaced FRBs are, because I could imagine in different ways it's constraining on both models. In the shock model, it's a problem because if one shock goes out and heats the upstream medium, subsequent shocks basically are hitting that same medium, and we know the maser efficiency is reduced. On the other hand, in magnetospheric models, if you have a first burst, you're going to really pollute the region around the source. And I think, and if we scale up from this FRB to a cosmological one, we're talking about a lot of energy dissipation in the magnetosphere. And it's just harder for me to understand how you get the second burst out of that environment. But anyways, so I think my question for the observers is kind of, what do we actually know about the wait time distribution? Because I've seen different things. I mean, do we see two classes, one of which is a very short duration that could be subbursts of the same pulse? And then I've seen these distributions where we have one that's a longer wait time. But I've also heard that maybe those are influenced by selection effects. And so I guess I'm just wondering, we really have evidence for this sort of bimodal population in terms of the wait times, or is one just essentially two parts of the same burst? I mean, clearly in the 1935 here, these are two distinct FRB-like things because they both produce distinct X-ray flares. But I guess I'm wondering in the broader population, what do we know about the wait times?
I think Bing raised his hand. Bing can comment on the wait time distribution.
Follow the discussion. I'm not going to comment on the waiting time. I just continue the discussion Brian raised. I think for the pulsar-like model and the shock model, difference is that for the shock model, indeed, the later ejected plasma will interact with the previously ejected plasma. But for the pulsar case, one can have, because the star is rotating, magnetosphere is rotating, one can have this simultaneously ejected bunches or whatever, but the first pulse you see is from an earlier phase, and as the star rotates to another phase, you see another one. So you do not necessarily to have the interaction between the two. So that's the concept.
But I get, my point is, if we really believe that 1935 was not a fluke and that every FRB is accompanied by 10 to the 5 times more energy in hard X-rays, it just seems to me that very shortly spaced FRBs, you just have a lot of pair production. It's not a precise constraint. It's just a feeling that if we boost 1935 by a factor of 10 to the 5, it's hard not to get a fireball in that environment. So
I think if I may just inject a very quick thought, I think, Brian, that's a valid point, and it's a good point. I have thought about it, and I think it can be done, but whatever it is, the point that you're making is a good point to make. And let me leave it at that.
I guess it's unclear how the plasma, basically electron-positron particles in the magnetosphere relax back to some original condition. That may indeed take some time. I'm not very sure if people who worked on the magnetospherical plasma can comment on this, saying that it's possible or impossible for the magnetosphere to relax.
Still, why do you really require the magnetosphere to relax? So it could be that in multiple field lines, such kind of bunches got launched, and X-rays are polluted everywhere, and they just break through, like what Kunihito Ioka talk about, breakout from the fireball. But you just the line of the star is rotating, the line of sight start to see these emitters in turn, and then you can produce multiple pulses.
I think it does pose problems.
So I see Andrei Timokin raise his hand. Let's hear about his.
Let's hear from them then. Yes.
Can you hear me now?
Yes.
I just want to make a short comment about relaxing after the burst. Let's see if something happened in the closed field line region and we have an overabundance of plasma. That plasma should carry a current in order to sustain some twist. And I would think that this plasma, which was in excess of plasma density, which is necessary for to carry this electric current, could simply precipitate on the neutron star surface. So I would expect that this could take like a few flyby time. On the other hand, if we are talking about like plasmon ejection, it could go simply into the pulsar wind or whatever wind this neutron star is producing. So I think that the relaxation time will be comparable to the dynamics, to the flyby time for the corresponding field lines. So, and then this, but yeah, so just, but then it is sort of would be comparable to the pulsar period, to the period of that neutron star. So whether it's comparable to the distance between successive pulses or not, it should be looked upon, so just in each individual case.
Right. Right. I mean, that's what I thought, Andre. That's what I, you know, that was a straightforward estimate that I did. And what you say, I agree that that is one-time scale. The problem is, and I think that is what Brian was suggesting, and he can, you know, jump in and say if I'm mistaken. If you have an X-ray, right, you have polluted this magnetosphere with a large amount of energy in the hard X-ray, then you will have this pair production continuing for the duration of the X-ray burst, which could be.
Agree.
That's the problem. I think
yes.
That is the problem that Brian is raising. Brian, correct me if I'm misreading your point.
Yeah, there's the issue of the pairs you create, and then there's the issue of even if Andre is right and the pairs are advected out in the wind. Well, I guess if they're moving faster than the almost at the speed of light, but yeah, I'd be slightly worried about some residual effect they might have on the propagation even later than they're produced. But yeah, that you could have a X-ray dissipation that lasts considerably longer than the FRB. Yeah.
Agree. Yes.
Okay.
Dorwar has had his hand up.
Let's go to him.
So yeah, so on the X-rays, so we all know that the pair production threshold is 1 MeV, right? And the magnetar burst that had the FRB, the cutoff energy was about 80 keV. So to make pairs from that, you're deep in the wean tail. That's point number one. Point number two is that you have photon splitting going on in magnetar magnetospheres, and that can operate down to about 50 keV. So I don't think it's as polluted as people think it is.
Andre? Yeah.
Yeah, I want to make one quick comment. I haven't posted a paper on Astro PH yet, but just would like to tell you quickly the result that I have. And the result is that if you send a very strong radio wave like we observe from FRBs, from a radius from inner magnetosphere, this near field emission scenario, then I find that the wave actually will not get out as it goes through the outer magnetosphere, through radii outside, like 10 to the 9 centimeters roughly. Because the wave amplitude becomes greater than the background field. And so the particles are no longer magnetized in the background field. And one can show, what my calculation shows, is that particles gain to very huge energies in the wave, and the effective cross-section for scattering becomes not suppressed by the strong magnetic field, but actually amplified by a factor of 1,000,000. And so that process leads to emission of gamma rays, and the wave chokes in the produced Pierre cloud. The wave, of course, also pushes out the magnetosphere away from the star. But when you do the entire calculation carefully, you find that this Pierre cloud is going to choke the wave. So in other words, the basic point is that even if you don't have an X-ray burst accompanied by some different mechanism, just you have a single FRB, which is strong, then it's going to process its energy into pure plasma before it can get out through the light cylinder. That's the result of the calculation.
Andre, thank you very much. I look forward to reading your paper. Now we are down to about 5 minutes. So which means we should start wrapping things up. Wenbin, can we go to the second last slide, which is slide number 37?
We haven't done this poll yet.
Oh, sorry. I'm sorry. My mistake. Yes, please do. This is an interesting one.
Yes.
Okay, so this is the final poll we have, and let us know what you think. Which problem we will solve first? Progenitor or emission mechanism?
Oh, so many people voted yes and yes. I cannot believe it.
I think we're biasing it. That's why we're showing them the results.
People are optimists. That's good. I like that.
Yeah, I shouldn't show the result before. Yeah.
Well, okay.
Okay, now we're back on track.
Wenbin, do you want to define what you mean by understand in this question? Brian.
Oh yeah, I personally would think, let's say if we know, what kind of typical property, or let's say for progenitor for the first one, what are the magnetic field strengths? Is it a neutron star or not? And what kind of young or old? Not like in the nitty-gritty details, but roughly know what it is. We feel confident to speak to the public audience that we know this is that kind of object is generating FRBs.
So if this definition changed your answer, you can I think you can change your answer as well, your poll, if you want. I'm sorry, Ben, you were saying something.
I was saying we probably have all of the answers already, and I was curious if someone from the no and yes camp wants to defend their point, because I find that interesting.
Actually, we are down to the last 3 minutes, and I don't think we have time to defend anything anymore. I think we should bring this session to a close, but do share these last 2 slides that the panel, not the panel, but Mohit and Wenbin put together. So I would like to have the people, see these slides. You can go to slide number 37. This is a to-do list for.
Try your mic.
I think I'm not eligible to to discuss this. Theorist should, one of the theorists should actually describe.
No, we're not going to discuss. We are just going to leave it. You can see this will keep your lives busy and gainfully employed for n number of years, where n is a large number. Okay. And the very final slide. Are we in a position to share the final slide, Wenbin, or not quite?
Well,
it's not.
Not quite.
No, skip it. Go back to this. We will leave it at this.
Yeah.
So if you have any last, like, pressing point that you like to make, please make in the next 30 seconds. Well, otherwise, thank you very much for your participation and interesting questions, lively discussion, and have a great weekend. And that's it. This is bye for now from the panel.